Good day and welcome to A-Level Physics. I know I've promised you guys to make a little video to just give us an overlap into the next part of chapter 23, Coulomb's law. So here we go. Okay, so guys, the first thing that we need to see is the following. Okay, we now know that Coulomb's law says that the electrostatic force is equal to the electrostatic constant Q1, Q2 over the distance squared. Okay. The next concept that we're going to look at is called the electric field strength. Okay. So we have the electric field strength, and the formula for electric field strength, if we bring the formula, F is or E is F over Q. Okay. Or yeah, Newton per Coulomb. Okay, so if we bring that formula in, we can see that that becomes my second charge. So I substitute that in the space of my F. It simplifies, and we get that the field strength is equal to the charge causing the strength and the distance between that point. Okay, so this is a specific point. Okay, and then we get two other things. We get the potential, okay, which is a V, and we're going to see that the potential is K Q1 over R, okay, and then lastly, we're going to look at the potential energy, okay, or they use a U here sometimes, okay, electrostatic potential energy, and where we have Q1, Q2 over R. Okay, so there's the four formulas that we're going to use. We've looked now at the first one. I've shown you where the second one comes from. Okay, before we continue with this concept, I want to take you to gravity, because gravity's got the same thing. Okay, we have the gravitational force, which is the gravitational constant, mass of the Earth, mass of the second object, radius squared. Then we get what we know as the gravitational field, and the gravitational field depends on the gravitational constant, the mass of the Earth, and the distance squared, and hence the mass of the object does not affect how fast gravity pulls it, proved by Galileo Galilei. Okay, so then we get the gravitational potential, okay, which basically tells us that it is the amount of gravitational potential energy, okay, or the amount of energy per kilogram. And then we get the potential energy, okay, so let's just call it gravitational potential energy, which is basically when I add my mass. Okay, so these equations are very similar. So once we look at here, we understand that the Earth has a gravitational field due to the mass of the Earth, and the further we are away from the Earth, the weaker that field will get. The same way a charge has an electric field, and the further we get from that charge, the weaker that field will get. Okay, then we get to this, and I'll show you guys how to derive this in a moment. But what we do here, we said that if we look in terms of space, this is now from chapter 18, using the Earth, just saying mgh, is not a good measure if we are measuring between planets and things like that. So they've brought this equation which basically states if you're very far away, it is a zero potential, okay? And then as you get closer to the surface of the Earth, the stronger the potential gets. Now this is the joules per kilogram, okay? Which means it is when there's an unknown mass, okay? That is relatively the amount of joules for every kilogram that the object has. The moment we know what the second object is, we can calculate the gravitational potential energy. It looks very similar, but the unit for it is joules. Okay, so in the same thing here, the potential, okay, and we can link this up to potential difference, and this is voltage as well. Okay, remember it's electric field. The difference in potential, okay, and there here we have two graphs. Okay, if we are bringing, so remember this is attractive. If we are bringing something closer, that then we will have to do negative work. Okay, so the amount of energy and the work is going to link up with the potential of the electric potential energy. But we are doing less work, okay, because it's attracting, so it happens automatically. The closer we bring the object to the charge or to the field. And then if it's a repulsive field, then as we bring it closer, it becomes more difficult and I have to apply more joules per Coulomb. Okay, now this is a theoretical place. It's a position, it's not a charge. It's not like I have a test charge that I bring closer. But the moment I have an actual test charge, then we can calculate the amount of electric potential energy, okay, that will take the amount of joules, or it's also equal to the work done. Same thing here, it's also equal to the work done. So now, when it's an attractive field, I have to do negative work, so it happens automatically. The closer I bring the charges, the more they attract each other. When it's a repulsive field, I have to push those two charges together. So the moment we have the known charge or the known mass, we can calculate the energy. But the moment we don't have it, when it's just simply a position, just a position in the field at this point, every object with a certain charge, okay, will have this amount of joules per Coulomb due to that charge. Okay, now if we know that this is 1 Coulomb, then we can calculate the energy needed at that point. Okay, so just to emphasize and explain this bottom part again, we are basically going to use a very easy example. My car has the potential, okay, to drive 12 kilometers per liter. Okay, and but if I have 10 liters, okay, then my actual distance is 120 kilometers. So this is the potential. But the moment I know how much liters I have, I can calculate the actual distance. Now it's the same thing when we work out with joules per Coulomb. If it says it's going to be 100 joules per Coulomb, okay, that is my potential. But if I know now I've got 100 coulombs, okay, sorry, it must be, Coulomb is a C, okay, sorry for that. If I have 100 coulombs, then I know it's 100 joules per Coulomb, so it's going to be 100 times 100, which is going to be 10,000 joules. Okay, let's think in terms of energy. If we look at a gravitational field, let's say the Earth's gravitational potential is, okay, let's not work with the Earth. Let's say it is 20, the potential is 20 joules per kilogram. Now, if I've got a 3 kilogram object, then I don't have to calculate the joules, then I can just calculate the gravitational potential energy. And then I times that, so that will be 60 joules of energy to lift that object up to this point. So if here's my house, Okay, so let's say at this level, okay, the gravitational field strength has a potential, okay, the gravitational field has a potential of 20 joules per kilogram, okay, but if I put the actual 3 kilogram object here, it would be 20 joules for every kilogram, so it will be 60 joules of gravitational potential energy. Okay, I hope that's made sense, and if you've got any questions, please let me know. Have an awesome day. Goodbye.